I will begin. I think it's time to begin.
And your pinky toe just like... Bro, your pinky toe would fit to that. Bro, but if you just...
I'll clean the board while this important conversation is ending. Let's see here.
No, because if my pinky toe goes to that, my whole foot as goes sideways and goes.
We need to settle these questions about the pinky toe. It's important. It's important.
Sorry, sir. This guy's an absolute. Hey, appreciate it.
Bro, you're the one talking about having the dogs out.
You're not crocking, you are not rocking. End of story.
If you're not crocking, you're not rocking.
Amen. There you go.
Huh.
You're like,
Interesting.
the bottom of my foot.
Well,
You got grandkids.
you've given me some things to think about. Let me begin with a word of prayer. Dear Father, we thank you for this time together. We thank you for this class. Just ask you to be with us today. Help us to glorify you in what we do. And just all to understand a little bit more about your creation, about Power Series, Lord. In your name I pray, Lord Jesus. Amen. So, let me get straight into it. So today we're talking about Power Series. It won't be the last day, but here we go. What is a Power Series? Definition. Given A sub n is an element of the reals for n equals 0, 1, 2, and so forth. And x naught is an element of the reals. We say f of x equals to the sum n equals 0 to infinity of an times x minus x naught to the n is a power series. Get out of my sight. With center, there you go. You deserve to live. Center x naught. Center x naught and coefficients A0, A1, A2, dot, 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 dot. All right. So like the nth coefficient here would be, A sub n. Right. So this is what a power series is. What is a power series then? So, remark, a power series is a function which is defined pointwise by a series of power functions. What's a power function? So a power function is just something like x minus x naught to the n is a power function, right? So like here, if we talk about gn of x equal to x minus x naught to the n is a power function. All right, this is a power series. There are other kinds of series. All right, have you guys ever heard of a Fourier series? So some of you are in electrical engineering. You guys are pretty invested in Fourier series, long term for your education, right? Something you want to understand pretty deeply. A Fourier series is when you take an infinite series, but instead of adding power functions together, you add sines or cosines together. That's what a Fourier series is. Fourier series are more sophisticated, and they're more nuanced. Power series is kind of the easiest kind of thing like this. But you already see that we already have some of the tools we need to analyze this, right? Because we know how series converge or diverge. We've got a bunch of tests to try to rein them in and control them, right? But surely the most simple thing we have for power series, perhaps, or for series rather, to work with is the geometric series, right? Problem 1 on test 2 you guys all proved. The geometric series result, let me be optimistic. I bet you did. I think everybody did, right? So what I want to do is I want to look at some power series which we can motivate from the geometric series, all right? So let's look at that. So I'm going to look at some examples via geometric series. So just to remind us throughout this lecture of the geometric series, let me remind you that the geometric series says the following. It says the sum n equals 0 to infinity of c times r to the power n is equal to, c over 1 minus r. If and only if the absolute value of r is less than 1, right? This is the geometric series. If we index it starting at 0. Okay, so my example 1 then is this. I guess I'll do it here. So example 1, let's let f1 of x equal to 1 over 1 minus x for, I don't know, the absolute value of x less than 1. So I'm going to look at that function. All right? So what do I'm going to work backwards, actually, mostly here. I'm going to work backwards. We have been engaged in the enterprise of taking a series and finding its sum, right? I'm going to turn the tables. Now I'm going to take the sum and make it into a series, right? Check this out. So f1 of x is what? 1 over 1 minus x. But what is that? That's the sum of the geometric series with c equals to 1 and r equals to x, right? So this is equal to the sum, n equals 0 to infinity, of x to the n. Identifying c equals to 1 and r equals to x, right? What does this mean? This means that we can write 1 over 1 minus x as 1 plus x squared plus dot, 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 dot. We can trade 1 over 1 minus x for this sort of unending polynomial. But there's strings attached, right? This is only good for where? Minus 1 less than x less than 1, right? So that's my example 1. Example 2. Let's look at f2 of x equal to 1 over 1 minus x, where 1 is less than x is less than 3. All right, so let's think about this. If I'm stuck with 1 less than x less than 3, I want to find a ratio. If I'm going to play this game, I want to find a ratio, right? Because I'm going to try to apply the geometric sum in reverse. So what I need to do is to kind of repackage this thing as subtract 2 across it, right? So if I subtract 2, I've got minus 1 is less than x minus 2 is less than 1, right? So that says that the absolute value of x minus 2 is less than 1. let me demystify this for you. We're talking about the number line. We have 1 here, we have 3 here, right? Where's 2? In the middle, right? I have 1 less than x less than 3, right? So x is somewhere in here. Could be on the other side, whatever. What is this saying? What does this inequality mean? How do you read this geometrically? How do you put this into a sentence? This says the distance from x to 2 is less than 1. This should not be surprising, right? If you look at that interval, if you pick x, it can't be more than 1 unit away from the middle point, right? Because the length of that interval is 2, right? Okay, so we know for this context that the absolute value of x minus 2 is less than 1. So can I make that, can I make that x minus 2 appear in my formula so I can do the same trick I did in example 1? Well, let me show you how to do that. f2 of x, 1 over 1 minus x. So I want to create an x minus 2. How do you do that? Simple. Add 0. So I merely subtract 2 and add 2. I know this seems kind of stupid, but it's actually profound. Like, this is a profound step. I didn't invent this step. I saw somebody else do it, and I've been doing it since then. So look, then you simplify this, and this gives you minus 1 over 1 minus parentheses x minus 2. Notice that this gives you 1 minus 2, which gives you a minus 1. All right? And I'm sorry, I should just leave. That becomes plus this, right? My bad. If I factor the minus up there, then I put a plus here, right? So just to emphasize the pattern here, what we're really looking at is minus 1 over 1 minus parentheses minus x minus 2. So we have to think of this as c equals to minus 1, r equals to minus parentheses x minus 2. But this is the sum of a geometric series, right? It's the sum of a geometric series like that. And so I can write that this is equal to the sum, n equals 0 to infinity, of minus 1 times minus parentheses x minus 2, close parentheses to the n. And so this you can clean up. See, because minus parentheses x minus 2 to the n is really equal to minus 1 to the n times x minus 2 to the n. So I can do that, and then I can also put this other extra minus 1 in here, and so doing, I get this nice clean formula, n equals 0 to infinity of minus 1 to the n power, n plus 1 power, x minus 2 to the n. There you go, that's a power series. So this function is also a power series if you tilt your head and squint, right? I would not, so like there's some language here which gets a little fussy. The function as I gave it to you, 1 over 1 minus x, is that a power series? Well, no, it's not, right? But after we do this work, we come to this expression. This expression is a power series. So maybe to be more careful, I really should talk about power series as being an expression, right? You could have two different expressions for the same function. You know what I'm saying? Maybe you don't. Like, I have f of x equals to x squared, right? But that's also equal to 3x squared over 3. And it's also equal to, 3x squared over 3 plus 13 minus 13. These are all defining the same function, but they're different expressions. All right, so in the same sense, the given function, the given expression is not a power series, but we have shown that it can be written as a single power series, centered where? Here x naught is equal to 2, and the coefficients, a sub n is what? Minus 1 to the n plus 1, right? So that's the coefficients in this case. So over here, what was my x naught? Example 1, we had x naught equal to 0, and my coefficient is kind of boring, right? A sub n is what? It's just 1. It's always 1. Right? So the a sub n is equal to 1. Does that mean that the series diverges? It doesn't. Because that doesn't have the same meaning as the a sub n we were just talking about before today, right? If you want, I could use a different letter here to avoid confusion, right? I could, instead of using a sub n, I could always use c sub n for the power series for a while, but then there's no reserved universal notation for the coefficient, all right? Just like we could be using k everywhere I'm using n at the moment. Yep.
On the step where you have 1 over 1 minus x minus 2 plus 2, how'd you get that to equal negative 1 over 1 plus x minus 2?
Algebra. So I get 1. This distributes to give me 1 minus 2. So there's a net of minus 1. So you'd have, in the in-between step, I'd have minus 1 minus x minus 2 for the denominator. Then I just factor that minus out and put it upstairs. So I have a net overall negative in the denominator. I just shift it upstairs. So there's that. Yeah.
Do you always start the summation at n equals 0?
If I'm using the geometric series in its standard form like this, yeah. There is another way to do that, though. Like this is equivalent to the sum, let's say, j equals 1 to infinity of c r to the j minus 1. And you will see that written sometimes. But notice that if you start the index at 1, then you're obligated to shift the index of the ratio in the formula. And I would say that that's not really advantageous to us, because at the end of the day, we're interested in power series right now. And we like our power series, we're pretty dogmatic about this, all right? The power series has to be an expression of this form. Like I'm just saying, we wouldn't say that 1 over 1 minus x on its lonesome is a power series. And it has to be in this form. All right? I mean, you can write it long form, and we'd still say this is a power series. Like if you had a0 plus a1 times x minus x naught plus a2 times x minus x naught squared, okay? Like that would still be a power series, all right? I'm not saying that it's the sigma notation necessarily needed for it being a power series, but it does have to be an unending series, unending sum of power functions with coefficients which are just numbers. This is important because we're going to state theorems that are true for power series, which are not true for Fourier series, that are not true for other kinds of series. So we need to know what a power series is as a first point of order. That's the first thing I'm trying to attack today. Okay, so what else can we do? You're like, well, let's do this example again. I'm like, okay, fine, we can do that. How about example 3? What if I have f3 of x, 1 over 1 minus x, for 1 less than x less than 5? Right? If I do this, well, if I subtract, instead of subtracting 2, I'll subtract 3. I've got minus 2 less than x minus 3 less than 2. Right? So in this context, I've got the absolute value of x minus 3 is less than 2. So what I'd like then is the absolute value of x minus 3 over 2 is less than 1. So in this context, this is a good, I could use this as the ratio for a geometric series because that quantity has magnitude at most 1. And I'll stop. I'm starting to go into the territory where you guys can't see what I'm writing, so I'm going to shift over to here. So I had my f3 of x was 1 over 1 minus x. And I've just figured out that the absolute value of x minus, what was it, 3? Over 2 is less than 1 for the given context, right? for 1 less than x less than 5. All right. And great. Let's do my trick again. So 1 over what? 1 minus parentheses x minus 3 plus 3, right? Okay, so that's the starting point. That's going to make an x minus 3 appear in the formula. Now notice what happens. They get a 1 over, let's see here, minus 2 minus x minus 3, right? But we can factor out a minus 2, right? So this is 1 over minus 2 times what? Times 1 plus x minus 3 over 2. Let me just make it very explicit in your face. You shouldn't be able to miss it. Minus 1/2 divided by 1 minus parentheses x minus 3 over 2. Pattern match. What are we looking at? This is c over 1 minus r, with c equal to what? C equal to negative 1/2, r equal to minus parentheses x minus 3 over 2. So given this context, right, we have that the absolute value of x minus 3 over 2 is less than 1. It's almost like you're choosing the domains for your examples so that this happens. Yes, it is. It's true. I knew it was going to happen, so I'm deliberately forcing us to the context where it works. I'll explain where this context is coming from in just a minute. One more example, though, before we do that. Sum n equals 0 to infinity of minus 1/2 parentheses minus x minus 3 over 2 parentheses to the n power. Now let's clean this up. Cleaning this up, we have the sum n equals 0 to infinity of minus 1 to the n plus 1 divided by 2 to the power n plus 1 parentheses x minus 3 to the n. Now I think finally we have an interesting power series, right? What's the center in this case? The center is 3, right? X naught, as I'm calling it, is 3. Now Stuart might not call it x naught. Stuart might call the center A or something. In my past teaching, sometimes I call the center point A. I do a power series centered at A. But I like x naught. I'm going to stick with that for now. X naught equals to 3. What's my coefficient? A sub n, in this case, minus 1 to the n plus 1 divided by 2 to the n plus 1. Right? So if you'll forgive me this going back up. So let me just write, I'm going to put that up here if you don't mind. This is equal to what? So we've got minus 1/2. That's the first term, right? If I plug in n equals to 0 into all this, the first term in the geometric series is minus 1/2, right? And then I have what? I have plus 1/4 x minus 3 minus 1/8 x minus 3 squared, and so forth. Yeah.
Where'd your 2 in the denominator under the x minus 3 go whenever you equal to the second summation?
It's right there. So that gives me a 2 to the n times 2. 2 to the n times 2 is 2 to the n plus 1. I consolidated my 2's, right? So, okay, so yep.
I'm still confused.
Uh-oh.
When you had 1 over 1 minus x minus 2 plus 3, I guess I just don't understand the algebra behind it.
The what?
Like the algebra behind it, because I thought that would just be 1 minus, I thought that the minus 3 plus 2 is 0.
It is just 0, that's true. And yet, it does something.
But how? I just don't get how you get that to equal like negative 2 minus x minus 3.
Oh, that's because 1 is a distribute. Minus to minus 3, 1 minus 3 is minus 2. So these two terms combine to give me that.
Oh, so like, okay, so it's active parentheses right there, I guess.
So yeah, if we can do this for 0, and we can do it for 2, and we can do it for 3, we should be able to do this trick for any center that we like, right? So let's try it for an arbitrary point. Can we do this trick for an arbitrary point? Example 4. Let's look at f of x equal to 1 over 1 minus x. And let's try to see if we can make this a power series centered at x naught. So find power series representation centered at x naught. So if you've understood the last 3 examples, this should not be surprising, what I'm about to do. Here we go, f of x, 1 over 1 minus x parentheses, minus x naught plus x naught. I added 0. And then I'll repackage this. So what I'm looking at then is 1 over 1 minus x naught minus parentheses x minus x naught. In order to apply the sum of the geometric series in reverse, I must create a 1 in the denominator. Right? That's the critical thing. In order to do this in reverse, I have to have this pattern, right? And you might think what we're currently doing is really kind of like a very specialized thing, that there's only going to be a handful of functions that are accessible by this technique. And you're right. It's really just a handful of functions that work like this, right? So this is a very special trick, but it is when it works, it can't be beat. And it's important because a lot of functions fall under this category. So that's why I'm starting with it. And also because we don't need anything that we haven't already done before this class to do this. This is totally based on what you derived in test 2, problem 1. So there is a subtle difference though, right? We're not doing it just for one radius. We're doing it for a variable radius, right? That's the trick. So if I factor out 1 minus x naught, how does that go? What's that look like, algebra? There's a 1 here, right? So you got that. And what's this term have to be if I factored out 1 minus x naught? You have to do what? You have to divide by 1 minus x naught. That's how you factor, right? You're like, but there wasn't a 1 minus x naught next to the x minus x naught to start with. Yes, I know. That's why we divided by it. Factor. And now we've got you can see what it is, right? We can see what it is. C. What's C? Well, fine. One more step. One more step. So this is equal to 1 over 1 minus x naught divided by 1 minus parentheses x minus x naught over 1 minus x naught. All right. So lo and behold, this is the sum, n equals 0 to infinity of 1 over 1 minus x naught times x minus x naught over 1 minus x naught to the n. Using the geometric series result with c equal to what? C is 1 over 1 minus x naught, right? And the radius here is x minus x naught over 1 minus x naught. Question. What I just wrote, is this a power series? I would say arguably almost. Not really, though. When we talk about power series, we need power function times coefficient. I still have work to do here. There's not a lot of work to do, but to make it formally a power series, I really should write it like this. Sum, n equals 0 to infinity, what do I got? Well, I've got 1 over 1 minus x naught to the power n plus 1, right, times x minus x naught to the n. There you go. Now we can see clearly that the coefficient a sub n in this case is exactly 1 over 1 minus x naught to the n plus 1. And more than that, if you think about your life, the last hour of it, well, excuse me, half hour of it, you can recover examples 1, 2, and 3 from this general formula. Check it out. Put x equals to x not equal to 0, what happens? What does a sub n become when x not equals to 0? 1. That's what we found in example 1. In example 2, we had the center, 2. What happens when you put 2 into this formula? You get minus 1 to the n plus 1, right? This is a funny thing, right? This is equal to 1 over minus 1 to the n plus 1, isn't it? Minus 1's funny that way. And then example 3, right? Example 3, see what happens when you put 3 into the formula? You get minus 2. See, this is equal to 1 over minus 2 to the n plus 1. You could put the minus in that. You could group it all together like that. I prefer to write minus 1 to the minus 1 factors separately as a general point of like bookkeeping, but when is this good for? You need the absolute value of r less than 1, which is what? The absolute value of x minus x naught over 1 minus x naught less than 1, which is to say that the absolute value of x minus x naught is less than the absolute value of 1 minus x naught. Can somebody tell me what this means in a sentence? What's this inequality, this red circled inequality mean in a sentence? Can you put it into words? What is it saying? Yeah.
Fraction x minus x naught over 1 minus x naught is less than.
The red circled one, though, in terms of distance. I mean, you're not wrong, but yeah.
X naught is closer to x than 1.
X naught is closer to x than 1. Yes. To restate it again, the distance from x naught to x is smaller than the distance from x naught to 1. Why is this happening? Let's look at it. Give you guys a second to write your notes while I'm waking this computer up here. Oh, updates, you gotta be kidding me. Yeah. Microsoft. All right, so let me find a place to graph then. What's the graph of the function look like? What is the trouble with this function? If we just look at f of x, if we look at y equals to 1 over 1 minus x, what's the one place, if you think about that as a function, what's its natural domain? Its natural domain is everything except for 1, right? X equals to 1, you've got vertical asymptote, right? And the graph of it otherwise, let's see here, if I plug in 0, I get 1, so it's got a y-intercept like here. So this guy looks something like this. Very crudely speaking. And so what we're finding is that if you find a power series that fits this function, right? the power series representation of it, it can't get past that vertical asymptote. That's what's causing these things to happen. Are we done updating? Okay, we're done updating. Oh man. Now it wants my username. What's next?
Probably the last one.
You guys know my computer well. Maybe you have a future in IT here or something. I don't know. Wait a minute. No, I want more for you. I want more for you. What? The people in IT want more for themselves too. Let's see here.
Oh, no.
Let's see here. I mean, there's a guy at my church that worked in IT for 14 years, and now he doesn't work for IT. There's a reason for that, you know. Where did that go?
The left side.
Let it not be said I didn't top hat today, right? I'm working on it. I guess I should probably have hit this. Ah! All right. All right, come on. You can do it. You can do it. You can do it.
Maybe a little bit louder, but it'll work.
You can do it.
Nope, I was going for it.
More
enthusiastic.
Yeah.
You're dead to me, Panasonic. I'll never trust you again. I don't care. I guess it's not. I guess I'll come around. 1006. You have 3, 2, 1. Let's see here. Where was I?
Yes! Speed! Come on.
Come on. I said open. Open, you dummy. Yeah, it's a work in progress, guys. So here is a picture. Why is it still not opening where I want it to? Just a second. I refuse to look at anything inside this stupid browser. It offends my sensibilities.
So you should just restart the computer.
Yeah, maybe it'll update again. Maybe that update didn't work.
Ha! Take that.
Like manually download the update.
All right, so here's a picture. Oh, what are you doing? No, just shut up. Just shut up. There we go. All right, so look, what I've done is I've graphed. All right, here is just the first 3 terms in example 1. The first 3 terms in example 2, the first 3 terms in example 3, and I've graphed those. Those are quadratics, right? But their applicability is limited, right? -1 to 1, 1 to 3, 1 to 5, respectively. So the one from 0, -1 to 1 is this blue dot. And as you can see, the actual curve is in red. As you can see, the power series pretty well approximates the curve, provided we're close to the center, right? The closer you are to the center, the better the approximation. The further you get away, the more it drifts, right? And it's pretty much got no hope to cross that asymptote, right? Now, over here, the other one in green is the one centered at 2. As you can see, it's tracking the green, the purple one centered at, which one is which? Set up here. The green dots is the one centered at 2. So as you can see, it's really close to the function at 2, and then it kind of gets away if you get further away. And then this magenta one here, that's the one that's centered at 3, and as you can see, it tracks a little bit further actually as it happens. Now we could make precise the error that the power series, truncating the power series has in terms of like what are we losing by chopping it off at 3 terms, right? Because these are alternating series. I think if you look at a particular x, so the alternating series estimation theorem would tell me how much we're missing by just using the first 3 terms. But of course, you also can just visually see it here since I'm graphing it, right? So this is the next step from Calculus 1, right? The first step in Calculus 1 was we look at a function, we replace it by its tangent line, right? So the derivative describes the best linear approximation to a function. Now we have a mechanism, perhaps, well, we're not quite understanding it yet, but we will find a mechanism to find the best quadratic approximation, the best cubic approximation, the best quartic approximation. And so by taking higher and higher and higher order polynomials, we'll get closer and closer representations of a given function, but only locally. See, because we're going to get stuck across things like vertical asymptotes. And sometimes there are hidden dangers, right? Let me show you a hidden danger problem. So let's check this problem out. Example 5. Let's look at g of x equal to 1 over 1 plus x squared. What's its natural domain? It is everything. As a real function, there's no division by 0 here, right? Is this a geometric series? Can we convert this to a series using the geometric series? Certainly we can, right? Look at it. So that's the sum, n equals 0 to infinity, minus x squared to the n, which is to say the sum n equals 0 to infinity, minus 1 to the n, x to the 2n. To write out in terms of explicit terms, you've got 1 minus x squared plus x to the 4th minus x to the 6th plus dot, 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 right? This is a power series representation for the function. Where does it hold? What's the radius? So here, we're identifying the radius for the geometric series as what? The quantity x squared, right? The radius is minus x squared. So you guys tell me, if I'm solving the inequality absolute value of r, which is the absolute value of minus x squared equals the absolute value of x squared less than 1, what's the solution to this? I mean, you could rewrite this absolute value of x quantity squared less than 1, and the square root is an increase. I mean, so anyway, this gives us that the absolute value of x is less than 1. What? How'd that happen? There's no problem for this function. Why is it that the power series only goes from minus 1 to 1? Sir Roger Penrose refers to this as one of the fundamental mysteries of calculus in his book, Road to Reality.
Is that a required reading?
No, I'm not done reading that book either. I got about 100 pages into it. It has taught me things about teaching calculus, though. I mean, like it's got its moments, but it's not exactly leisure reading. So I don't really. Okay, so the trouble with you guys is you keep it real, right? That's the problem. See, because if you take a complex view, if you look at the complex plane, right? So like the complex plane, and you look at this instead of as x, if you look at it as a function of g, if you look at it as a function of z, where z is equal to x plus y, iy, in that context, there is division by 0 at plus or minus I. See that? These are problematic. And it turns out that when you look at power series from the perspective of complex analysis, the domain for a power series is a disk. All right, there's a disk. Now what happens on the edge of the disk is complicated and nuanced, but there is a disk of convergence. And so because we're looking at the power series here centered at 0, the furthest you can go out is 1 radius, because that's how far I is from the origin. That's why we're hitting the end of our applicability at plus or minus 1 in this real case. Because like it or not, what's real is connected to what's complex. And to truly understand real calculus, you have to understand complex calculus. That's just the truth. Unfortunately, we don't require it, but we do have a course here, Math 331. Shameless plug. I'm teaching it, I think. Well, I don't know. That's premature. Maybe I'm teaching it next year. Okay, so great. So we have these examples. The larger question is, how do we decide the domain of a power series? Right? So how do you think we should do it? You're like, you have 3 minutes. You can't possibly do it in 3 minutes. Oh, yes, we can. Check it out. This is the power series. 2 minutes. All right, I'll write faster. an x minus x naught to the n, right? So look at this. This is a series, right? When does it converge? This is a series. Think of all of this as the nth term in your series, right? We have a ratio test. So we just look at the absolute value of Cn plus 1 over Cn. How does that work out? That is an plus 1 x minus x naught to the n plus 1 divided by an x minus x naught to the n. But I'm taking absolute values of all this stuff, right? So you do the algebra. What do you got? You've got the absolute value of an plus 1 over an, right? Times the absolute value of x minus x naught. This is what we would consider for the ratio test of the series. Think about, how does this have to go? What are the different possibilities? Well, there's 2 different things going on, right? To make we need what for this to converge? We need this to be equal to rho, this to go to rho, right? We call it rho for the ratio test. What are the possibilities here? First of all, if x is equal to x naught, is rho less than 1? Yes. Congratulations. Every series converges at its center. Every power series, rather, converges at its center. So that's always in the so-called interval of convergence. What happens, though? If this limits to something finite, right, then you can make this small enough to make that less than 1, right? So like, suppose this works out to L. Then you need this to be at most 1 over L. So you're looking at x, the absolute value of x minus x naught less than 1 over L. What is that? It's an open interval that goes plus or minus 1 over L from the center. So the other possibility is that if this ratio of coefficients works out to something constant, you've got an open interval centered at x naught. What's the other possibility? The other possibility is that this ratio goes to 0. If this ratio goes to 0, we don't care what happens to this. If this goes to 0 as n goes to infinity, independent of this, that means that rho is equal to 0, and therefore it converges. Those are the 3 cases. Either the interval of convergence, which is the domain for the power series, is a point, it's an open interval, or it's everything. That's the domain of a power series, ignoring the endpoints. So I'm talking about the open interval of convergence. It turns out, when the ratio test is inconclusive, we have to fall back on our other methods. But that's it. That's it for domain of the power series. Actually, that's it. Anyway.